I'm going to show some highlight, not all the highlight, but very few of them, because there are many, about what nanoscience and nanotechnology you could do with graphene and on silicon carbide surface and interface. And I say a few words about art also, how it could be related to art. You will see, I felt I couldn't resist. So let's move. Okay, so question, the Moore's law, where are we? You know that since the 50s, every 18 months, the number of data that we have to store double. It's like that since several decades. And you have some figure of merit, and the problem is you go down, and where is the light here? Is it no, it is? No. Okay. Okay, we're talking. So you can see that we go down, but we're reaching some limits. You have some idea of the device that has been developed by various companies, including IBM, Intel, and so on and so forth. The problem is not, are we able to make things smaller and smaller and smaller? That means we have the downsizing approach, or a bottom-up approach where you assemble by nanotechnology atoms to make and to develop, you see, a structure which could be used as an active device. The problem is the following, is that as soon as we integrate that, the problem is evacuate the calories, and that's the major problem actually, because you need to go, actually we are here, and when you use your laptop on your knees, you feel that it's a good radiator to warm your knees in winter, especially in Marseille today, because it's not tropical, frankly speaking. And then we are going where? To the dissipation of a nuclear reactor, to a rocket nozzle, and up to the surface. So that cannot continue like that. So the problem is not to make things smaller, smaller, and smaller. The problem is to evacuate calories. And the bad news is many semiconductors do not evacuate calories, especially you see the most famous one, the silicon, still it's silicon. Things change with silicon carbide, which has a thermal conductivity of copper, and change also with graphene. We are going to see that. So we started to work onto that with a company led by Eric Wimmer, which is materials design at CEA, and we have a PhD student that is first paper in the field, where he starts to develop a method to measure the thermal conductivity. The paper just came out this month, and that's something very interesting, but it has been addressed by various papers before, but this is a new method which is extremely strict. Actually, to measure the transport property, you need primarily theory at this point, because practically speaking, experimentally, it's another problem, but we have some idea on how to do it. The Moore's law, more than more. You see, so the semiconductor industry will soon abandon its pursuit of the Moore's law. That just came out in Nature, and you can look at this paper. There is a reference, I can pass it to you. It just came out actually this month too. And it's something interesting, because it means that we have to look to something else. Now, what is the structure of graphene? Graphene, this is, you have many type of single layers. So you have the fullerene, you have the nanotube, and then you have graphite, and graphene is just a single sheet of a single atomic layer of graphite, which could be, you see, just like that. Graphene is a zero bandgap semiconductor, so it's a semi-metal. Graphene is a single atomic layer of graphite, and so it's just a surface. It's, therefore, it needs a substrate. That's mandatory. And for instance, making some function very well known in electronics, that making a ohmic contact, start to be a big problem there, because if you make a ohmic contact, then you're in trouble because you destroy, you're obliged to destroy the structure of graphene, and you're in trouble. So graphene could be obtained by mechanical exfoliation, which is a TET method. Just between us, do not repeat to anybody. When I started my first PhD program several decades ago, I used my PhD advisor want to make me insertion of bromium into graphite. And he asked me, show me how to make that by you know, with a tape, to have a thin graphite layer, to use it to look at electron microscopy. So I did that the first time, and I put it, and I say, okay, the first time I do that, they say, okay, Soukiassian, you're good. Oh, you did good. But where there is something like hole, what did you do there? You are too much brittle. It's not a hole. You have just one layer or two of the. So I didn't know graphene exists, so it's like that. So as I told you, graphene needs a substrate. So it's a single layer. That just was the way it looks like. Now, the first time I heard about graphene, the word graphene, was here in Marseille. I was in the PhD committee, I think with Guillet, you were there, of Isabelle Forbeau, led by Marc Temelin and Jean-Marie de Bever. And she was investigating graphite on the 6H SiC silicon carbide surface. And then she put very clearly growth of the first graphene sheet may proceed on the top. That's the first time I heard about that. That was in 1998. Okay, she didn't get the Nobel Prize. I regret it, but it was interesting anyway. So now let's resume on this slide. Epitaxial graphene. You see, it's nice to have graphene, but you need a substrate. What is good about silicon carbide? Silicon carbide has more than 10 different surface reconstruction. You see, I don't have time to show you that. From silicon rich to carbon rich. The graphene termination is one specific surface reconstruction. So practically, it's ready to go. Well, it's not that simple. And a good method that has been developed by Walt de Heer and Claire Berger, and she's a French working there, from CNRS working there. And they at Conrad and many others, and we worked with them. And so they developed the so-called furnace method. And when you look at what was predicted, it's a quasi-particle dynamics, you find a very strict, almost ideal Dirac cone. But other methods have been developed in Germany by Thomas Seiler and co-worker. And it has also been developed, that has been developed on hexagonal silicon carbide. This is on cubic silicon carbide. The first one who did that was Victor Aristov. We worked with him. He visited Marseille. He visited my lab many times. We worked together. But also by, at the RIEC, by Maki Tsurumitsu, who developed also this kind of method. So, what are the highlights of that? Bon. The transport properties are outstanding. It has a very large fast coherence length, over 1 micron at 4 Kelvin. It has unprecedented high mobility. You are talking about 250,000 centimeters square per volt second. Compared to silicon, it's order of magnitude above. The charge carrier move just like photon at zero mass and constant velocity, just as photon. And I will say a few words about that. It has unsurpassed spin diffusion length exceeding 100 micron. That has been done in the University of Paris-Sud and at CNRS and at the lab of Thales by Albert Fert, good colleague, Physics Nobel Prize, and Albert explained me why it was very interesting, and I will say a few words about that later. It has a thermal conductivity which is 10 times higher than copper. So remember what I told you at the beginning, this is a very good thing. Also, it's mechanically the strongest material ever measured. It goes well beyond any deformation. So it has outstanding property, but graphene, you see, is now on the roadmap, which is meaningless because, as I told you, you have to evacuate calorie, but precisely, it can maybe evacuate calorie. Then, just to show you, this is the first direct observation of a nearly ideal graphene band structure with very strict, you see, Dirac cone. You can see how straight it is. And when you are on a carbon face, you have several sheets of graphene which are strictly decoupled, one from each other. So that has been done on a sample coming from Atlanta, from the Georgia Tech. We did that. Now, graphene steps and application. But when you have a new material, what do you need? The first things you need is to have the material. So there are several ways to do it. The mechanical exfoliation, epitaxy on silicon carbide, CVD on metal or insulator, transfer on insulator, then you need to transfer on an insulator, or by chemical exfoliation. Then you have two problems. You need to functionalize it. So one thing is, you see, I told you it's a semi-metal. You need to open the gap. You need to dope it. You need to create a graphene metal interface, which probably is the most challenging point. You need interface passivation, and recently, I don't have time to show you that, there are graphene nano ribbon on which you can, you see, open the gap in this way. And you have application, which I would call it low-tech, quoted, which is, for instance, touchscreen, such as touchscreens technology. But on your screen, you can just push it, and that's very interesting. Infrared and terahertz laser, that's high-tech, and supercapacitor, which could be used for energy storage. And you have application, electronic device, pintronics, graphene metrology, sensor, NEMS. And for application, graphene needs to have a substrate, so we can potentially look at that. Now, the problem is, sometimes you have this. What is this? This is a nice graphene sheet that we grow on a silicon carbide surface. And on this step, you can see there is something. If you make, you see a height profile this is done by STM. If you make a height profile on that, you see it just forms mesa with a steep side. And what is this? If you do Raman spectroscopy, and this is carbon nanotube. Now, if you look at that, it looks like aboriginal painting at the nanoscale. So this is carbon nanotubes that are very vertical. If you go to the next steps, you can see another look at this nano object as aboriginal painting. So you can see this is a nano ballerina, I call it. And this is a sun white lady that is observed in Botswana. And this is another thing. You see this nano object, and so this is sun. Also painting Bushman that you can observe in Namibia. I saw some of that in South Africa, but well, that just, it's an art related, so I guess it was mandatory to, this is the main things, because normally it's a defect, it's a problem, but you don't want to have that, but here it's become an opportunity after all. Well, very good. So let's continue now. Nanochemistry. Silicon carbide is a very, the problem is to, you see, functionalized graphene. You cannot work too much on the graphene, you have to work on the substrate. So now if you take the silicon carbide substrate, there is one thing we found which is extraordinary. You know that that's the work of my PhD student, Vincent Deric. I want to study hydrogen, so we saw that hydrogen decorates the dangling mode at the surface of silicon carbide. And I say, you do STS, and he looked at the STS, and he said, but well, the gap is closed. It looks like it's a metal. It's metallic. But I said, that's very interesting. He told me it's impossible. Hydrogen is supposed to passivate semiconductor, not to metallize. He was engineer in electronics. So I said, well, it's very simple. If it's true, just ask oxygen, put oxygen, you are going to remove the metallicities, and we will see if it's real. He had oxygen, and then the gap did not open, so I was a little bit puzzled. And then we did the photoemission spectroscopy using a UV lamp and electra light source. We clearly create a Fermi steps. So it's metallic. What is interesting, it's not only metallic, it's also resistant to oxidation. That means you can do two things at the same time, passivate and metallize, which create a big interest in to medical science, because they, in a conference, somebody come to me, this is what you did, you're very interesting, what you're interested in too is that. Yeah, well, but what do you do? I am in medical science. So he explained me that it's very good for interfacing with, you see, biocompatible material. Now, we also study that by vibrational spectroscopy and by photoemission spectroscopy, but also by calculation made by Eric Wimmer that I mentioned at the beginning, where we saw that by this simulation and in excellent agreement that hydrogen open nanotunnel below the surface of silicon carbide, and in which, if you look at the 3D dimension, you have dangling bond. So this is decorated with hydrogen. You have dangling bond which could welcome any metal, any molecule, which could passivate indirectly the graphene layer, which is deposited on top of it. So that's something very interesting for functionalizing. So concerning this, we could say that we have shown that hydrogen create open nanotunnel, and of course it's extremely interesting to, you see this point, because dangling bond located inside the nanotunnel offer a unique template to capture atom and molecule, which is especially interesting to functionalize graphene on silicon carbide. Now, application. There are many types of application. I have about 10 or 15 slides, but I show you only 2 or 3. 100 gigahertz transistor from wafer scale epitaxial graphene that has been done by Fedor Navoris and his group at IBM. And then we come on to that. So that has been done in the group by Bruno Lubac, Marie-Hélène Blanchard, Pierre Senior, and Albert Fert, Physics Nobel Prize, who show that graphene has unsurpassed spin length diffusion. You see, it's much larger than the diffusion of the electron. So I was a little bit puzzled to understand that. How could it be? Well, the spin continue and transfer to another electron. And why it's interesting, and that Albert Fert explained me that, why it's extremely interesting. It's extremely interesting because it's very low tech. He said, we don't need to make anomic contact. You just have an injection barrier. You put that, you see, on an insulator substrate, SiO2 or whatever, what you want. And then you just need an injection barrier. It's not very sophisticated. So probably spintronics is the future of electronics, because in that case, you have something which is unattended. So we have to keep that in mind. You have also many type of sensors. So I remember this one. You see sensors that for biosensor, many type of sensor. So you can find there is a reference. Since if you need the reference, I can pass it to you, of course. So now let's move to something else and go from the nanoscale to the year-light scale. We're going in the space now. Silicon carbide and graphene in the universe. Question, how life came in the universe and on Earth. What could be the prebiotic route of life in the universe? How organic species appear in the universe, which is mandatory to explain how life came. And so hydrogen, oxygen, silicon, carbon are the species the most present in the universe. And so they make silicon carbide exist also in the universe, because we find it in meteorite in the Diablo Canyon in Arizona by a French pharmacist, Henri Moisan, who got the Nobel Prize, but not for that, because he found fluorine. And then I didn't knew anything about that. People from Madrid contacted me to give a seminar, and they explained me that. You see, so this is pH in the universe. If we find pH, how pH is formed, we know that could be derived to organic molecule, which could be a key step for prebiotic route of life. And then they told me, so this is a pH, so it's just a graphene layer decorated with hydrogen. If you move there, so we did, they told me, could we do experiments? So experiments were done by STM, and when you put hydrogen create, you see, this is the steps, and it removes these things, and you have pH. So it leaves, that's the first evidence. The second one is this one. You see experiment using synchrotron radiation, and you see that sp2 is developing there. So silicon carbide braid etching in the interstatement as a possible path for polycyclic aromatic hydrocarbon, possible route for prebiotic root life in the universe. So this is the general scheme. You see, you have several type of, things, and they show me that, and 4 minutes? Okay, yeah, I have almost finished that. Yeah. And then they show me this, and they ask me what I think about that. He says that's what's happening in the universe, we believe. I said, do you know that? Well, we make observation, and I say, do you have the temperature? So, okay, we'll give you the temperature. You look at this web. This is the temperature. I told him, so what do you think? He said, I have a good news. On Earth, it's exactly the same. In my lab, when we do that, it's exactly the same. So it's really something interesting. We are in the year right. We are not anymore on the extreme light, but that's interesting. So you can look at some book, some special issue we edited in the MRS bulletin with people from the US Air Force Research Lab. I gave also an interview about that at the IOP in London. And so I mentioned also all my co-workers. There are many, of course, and especially people from Madrid, people from United States, and people from France, and Eric Wimmer. And then let's talk about science by the rapid slide. Eric Wimmer is a theoretician, so he's co-founder of and chief executive officer of the materials design company. He's a chemist, a physicist, and also an artist, a painter. So painting is representing from three-dimensional to two-dimensional. So this is Versailles. This is mountain probably in the Alps. This is in Brittany. And then he's a composer. And he's a piano player. So from 2D, he passed to 3C. And he also developed a method with plane waves, FLAPW plane wave, which was very famous, and we start to collaborate with him. Now, relativity theory by Einstein. I'm not going to develop about relativity, you know what's relativity. But then the soft watch developed by Salvador Dali. I visited this museum with my wife in St. Petersburg and in Figueras. And this is a soft watch. And actually, you know how it came this idea? He discussed with Albert Fret. So Albert Fret is a Catalonia from France. He's from Catalonia, from Spain, so they meet. And he says that, well, he inspired me. And even, you see, their museum sell watch which are soft, and my wife bought one. So now she's always late. So. And finally, I would mention another scientist and artist, Paola de Padova. She's here. And she paint, you see, so 3D to 2D, these kind of things. And you know in what museum is that? In my office in CEA Saclay. Thank you very much. Sorry if I've been too long.
So you discovered graphene before a game?
Oh, no, I didn't know it was graphene, you see, it was, I made that, now I remember that, but at that time, the know-how, that was a failure. I mean, that was, I get a lecture from my PhD advisor, told me, you're not delicate, this is incredible. He was very enthusiastic at the beginning, but then it became very badly. But anyway, yes. So, no, I made that, so when I learned the discovery of graphene, Geim and Novoselov didn't get the Nobel Prize for discovering graphene, but most people think that it's because they highlight the properties of graphene, which was interesting, you see. So.
Okay. Thank you.
Yeah, Suji.
The graphene is useful for painting?
For painting?
Yes, you can make a painting on graphene.
Well, I haven't thought about that. Bon, I will think about it. Nano painting.
I guess, but this is for our Chinese friend. I think that what we call encre de Chine, which is China ink, probably contains graphene.
Well,
don't you think so?
Hey, it's a liquid form. It's not. It's liquid. It's not a solid state. Okay.
Yeah, I think it's probably graphene inside.
Bon, let's think about it and make a proposal.
Thank you so much.